Hello, I'm Oscar Romero, and this talk is on the paper A Task-Oriented Dialogue Architecture via Transformer Neural Language Models and Symbolic Injection. This paper is co-authored with Antian Wang, Aaron Steinfeld, John Zimmerman, and Anthony Tomasic. Recently, Transformer Language Models have been applied to build end-to-end task-oriented dialogue systems. However, there are still some challenges that need to be addressed. For instance, usually, these kind of approaches perform poorly on context retrieval and symbolic reasoning. Also, they operate only at the text level. We address those limitations by leveraging transformer models' versatility to generate more complex constructs, such as symbol representations, embedding the model in an operational loop that blends both natural language generation and symbolic injection. To this purpose, we use the DSTC8 challenge dataset that contain over 20,000 multi-domain dialogues. We first pre-process the data by encoding dialogue annotations into sequences of symbolic representation segments using a prologue-like syntax, and then intermix them with natural language. Then we fine-tune end-to-end a pre-trained GPT-2 transformer model. Finally, we broke down the generation process into three main steps, resembling the execution of a pipeline dialogue system, except that inputs to each module are composite structures of symbols and natural language. This architectural breakdown allowed us to add new experts that intercept each module's outputs, manipulate the corresponding symbols, and inject the updates into the context maintained by the system. This is our proposed system architecture. It resembles a blackboard architecture, but let's see how components interact with each other. First, both user and system utterances are processed and stored in the blackboard. Then, the forget module ensures that the sequence of inputs doesn't surpass the maximum limit of tokens that GPT-2 can process at a time by forgetting the oldest non-symbolic text in the history. Next, GPT-2 takes the dialogue history as input and generates a symbolic dialogue state and a service call as outputs. Next, generated symbols are injected into the blackboard. So, given a user utterance like this, I need to take a bus from Las Vegas to San Francisco. The system will generate a prologue-like syntax representation for both the dialogue state and the service call, as shown at the bottom side of this slide. Then a slot value validator checks whether the dialogue state symbols were correctly predicted. If not, corrections are done, and symbols are reinjected into the blackboard. Given a generated service call, the service executor queries the database and publishes the results on the blackboard. Based on the current context, the dialogue policy module uses the GPT-2 model to generate the next system action. For instance, this will be the symbolic representation for an action that provides information given a prior user request. Finally, taking the current context as input, the energy module uses GPT-2 to generate a natural language system response. For our experiments, we use the open source implementation of GPT-2 small transformer model. Also, we use the default values for ADAM learning rate and ADAM optimizer. To generate more coherent text, we set parameters top P nucleus sampling to 0.95 and top K sampling to 50. As dataset, we use the schema-guided dataset proposed at the DSTC8 challenge, task number 4. This dataset contains rich annotations across the whole dialogue pipeline, and its size exceeds the existing dialogue corpora in scale, with over 20,000 multi-domain task-oriented dialogues. We carry out automatic evaluation of our system on 2,300 dialogues using diverse metrics. For DST, we measured average goal accuracy, joint goal accuracy, active intent accuracy, and requested a slot F1 score. In addition, we extended those metrics to measure system actions in a similar way. For example, service call accuracy, joint parameter accuracy, and joint system action accuracy. Also, we use success rate for system performance and blue score for fluency of the generated response. Finally, we run an error analysis that let us identify the kind of error that affected the system performance the most, allowing us to build a simple heuristic-based expert that corrected errors while improving overall performance. We ran 3 different experiments. Experiment O, which uses the ground truth value or oracle value of both user and system utterances. So our results can be compared directly to the DSTC8 published results. Experiment G, in this experiment, history is composed of goal user utterances and system-generated utterances. This experiment captures cascading errors that propagate from earlier steps to later steps in the dialogue. And finally, experiment V, which is a heuristic-based slot value validator, which is added to the experiment O to improve performance. This experiment measured the impact of mitigating the most critical errors from the error analysis by manipulating symbols generated by GPT-2. Overall, our system ranked among the first half positions in experiment O and the first 2/3 positions in experiment G. From the table, it can be seen that our system outperformed other models on intent accuracy. Correctly predicting the intent demonstrates the ability of our system to track user intentions and effectively detect domain switches. Finally, experiment V made an improvement in joint goal accuracy of 21% and 43% over experiment O and experiment G, respectively. From the following table, experiment O mainly improved joint service call parameter accuracy, success rate, and blue score over experiment G by 18, 13, and 26% respectively. Clearly, some downstream error propagation occurs. On the other hand, experiment V slightly improved joint service call parameter accuracy by 8% over experiment O, due to fixing some of the dialogue state tracker issues, also improved the quality of predicting service parameters. Finally, although blue scores are low, they are paired with high success rates. In fact, a close inspection of system utterances indicates an overall high quality of language generation. In this paper, we empirically demonstrate that several capabilities of transformer language models can be leveraged to construct a new dialogue architecture that is more flexible and simpler, resulting in much lower engineering cost, and extensible, allowing symbolic injection and manipulation, while retaining reasonable performance. This work was supported by the National Institute on Disability, Independent Living, and Rehabilitation Research. Thanks.